let's welcome Jiahui today, and he's from UPenn Grad Lab. He has do lots of amazing research on 4D dynamics, and let's see, and he's definitely the kind of person you come with to talking to. He has like lots of driven personality, and that's why we have so much high participation here. And today he's presenting his talk on 4D vision, presentation, reconstructing generation, and the dynamic dynamics. So let's see. And he's definitely.
Thanks for this very warm introduction, and I'm very happy to here to present some kind of my previous research on 4D vision, how we can represent, reconstruct, and generate the dynamic 3D. Thanks for this very warm introduction, and I'm very happy to here to present some kind of my previous research on 4D vision. Okay, so I'll jump my introduction here. I will first thanks for this very warm so that it's very important to model the important dynamic some kind of my previous research. There are several facts for our next okay, so devices, glasses here, centric devices, we all operate in this dynamic egocentric environment. So that is very important, very robust, capturing algorithms of systems to create the content for this ecosystem. There are several facts and also for the all devices, self-driving cars, egocentric devices, we all operate work, and usually you need to understand this dynamic process to learn cube and very robust, capturing algorithms of systems to create the content for this ecosystem. There are several facts and the dynamic also for the devices can be continuously generated from the sensor in the real world, and usually and maybe understand in the maybe in the near future the data for the text always may be consumed by the large models. But still we are not at the point, and the dynamic for the video data more further like 3D or 4D can be generated from the sensor in the real world, and finally like this kind of near future video models primarily they work in pixel space without any by the large models. Basic modeling of the still we are not at the point. Here the 3D or the 4D video data very easy to make further artifacts or even just very sensitive to make this, and finally physical like possible. This kind of so it's very important to model this primarily to what space present today without any control vision, and I can briefly give you some abstract of what we do. Very easy to make first we study how we can represent very high degree of freedom and we can make this, and finally all the things possible. This kind of so we can learn to model for objects what present today observation of 4D vision, and I can molecular cameras, multiple cameras, and finally given this reconstructed data or predictions how we can generate or create this 4D content and predict all the things what may happen in the future. So we predict model. This is like the definition of observation we talk about in this molecular cameras, and before I talk into what finally given this reconstructed data or projects how we can generate about the philosophy behind predict kind of things what may happen. So basically imagine the first problem. This is like the dynamic 3D definition purely we talk about other than molecular because before I talk into what you mentioned of this problem solution space is a type of project. Things can move, can evolve. It's not about the philosophy of rigid camera motion. So we need to exploit some kind of structures or geometric inductive biases at a proper level in this modeling process or in this more than data-driven systems like the large neural networks. So we will see different structures in the following. This is the overview of the content of today's talk. First, we will see the structure of well-behaved invertible deformation field that we can use to represent like deformable object or things, especially in the context of nerve or occupancy this kind of volumetric permutations, which exploit this invertible nature of real-world deformation. And the second, we will see another very useful structure or nature of real-world deformation field that is useful in modern Gaussian splatings, which is this low-rank or compact structure of the deformation field. And finally, I will briefly present some works that further exploit the category-specific prior knowledge, because in real world, many of these deformable objects or 4D objects, they belong to specific categories like human, animals, or even maybe stricter multibody objects like the furnitures, the chairs, the articulated objects. How we can build this kind of structures into the modeling. Cool. So the first part is about this invertibility or invertible network. And this is CaDeX learning canonical deformation coordinate space for dynamic surface rotations with neural homomorphism. So basically, the term homomorphism here is a mathematical term that means continuous and invertible functions. This means real-world deformation usually preserves topology and never corrupts. So let's briefly warm up this. So this is a typical paradigm for DynMF or for dynamic rendering. Basically, you have a deformable scene and you want to form maybe some rendering of a viewpoint, and you can query around the array and ask what is the radius of each point. Basically, you will have a deformation network, which is an MLP that deforms this coordinate into a reference, or we call canonical space. And then there is a nerve inside this canonical space that can infer you the opacity, the colors, the radiance, anything you want. But there are several problems in this paradigm, especially with this MLP model of the deformation. So on a high level, I would say when we consider how we represent or how we design a representation of the 4D, we usually maybe two aspects is very important. One is how we associate information. That is how we model the correspondences. And the second is how we aggregate information. That is how we fuse all these partial observations into a consistent global one. For this correspondence, MLP is not consistent. For example, if you use MLP to model deformation field, you can deform from time 0 to time maybe 10. And then you use the same network to deform from time 10 to time 0. You will not find this kind of positions are the same. And usually this is formed as a cycle consistency problem. You enforce some kind of cycle consistency. And second problem is this canonical frame is usually heuristically chosen by for example, the first frame. You aggregate all the information in the first frozen frame, which cannot be determined by data or optimized through the data. So CaDeX is a work that addresses above two issues by introducing a novel factorization of the deformation. The idea is briefly this is a deformable object, and there is a point on the foot that is deformed by a well-behaved deformation function from I to j, j to k, k to I, to any combination you want. If you model in that space, you need to learn this MLP from I to j, j to k, and in this combination of any two frameworks and enforce this cycle consistency. Instead, we can factorize all this deformation with this kind of triangles. So for example, from I to k, this point is first deformed to a canonical space, UVW, through a canonical map we call it, HI. And then you do an inverse of another map, HK inverse, and deform to the time k. So every time you go through the same shared canonical point, and this can make sure this deformation is always cycle consistent. So in this case, the canonical shape can be represented in this kind of induced canonical space with a standard occupancy field. So here, with this triangle formulation, you can always get a consistent correspondence. But now the pivot comes to how to make this H invertible, because common like MLP, you input XYZ, your output may be something. And this function is even not invertible sometimes. For example, you map all the points to 0, and this is not invertible. So how we can make sure this H is modeled by some network that is invertible? Here we introduce this idea from the classical generative model, something called normalizing flow, some network called real MAP or a degenerate version called NICE. That is learnable, it's very simple, and it's guaranteed the deformation can be inverted. So how things work? So basically, the network, the input of the network is a coordinate, x, y, z. And the goal is output something UVW. Maybe with some condition, like a global, maybe some latent code, to decide how this network behave. And the idea is very simple. You just change the coordinate partially at each time. So basically, the network is a stack of blocks. We call it coupling blocks. And for example, at the first coupling block, you said at the initialization, I decide we only change coordinate z based on xy. By plugging this xy and maybe some global condition to a small MLP and output scaling and translation. And you apply a simple affine function to the z. And now you get a new z. So now it's x, y, z prime. You can change maybe x in the next block, and you can iteratively change every coordinate in the later like blocks. So why this function is invertible? So let's say first, this first block is invertible because during the inverse, you know xy is not changed. So you can get the same xy and the same c and get the exact same t and s. With this z prime, you just minus t and divide the s. Now you can recover the exact same z. Because each block is invertible, the composition must be invertible. That's to say, when you do the inverse mode of this network, you input UVW, you will get exactly the same XYZ. And this network is as simple as an MLP by just constraining the transformation to be partial on the coordinate. So mathematically, you can prove this can preserve the topology of the shape. It's a cycle-consistent. And if you degenerate this transformation by removing the scale, which is called NICE, with only this translation, you can prove the volume of the shape is preserved because the determinant of this Jacobian of this mapping is equal to 1. So basically, we can implement this this idea to do a task of reconstructing shapes from point cloud or some sequence observations. Basically, you input a sequence of point cloud. The goal is to reconstruct the shape of this object. I will very quickly go through this. Basically, you have an input point cloud sequence. You have some encoder, like a point net or some kind of trajectory encoders to get a per frame global latent that define the deformation state. You use that previously discussed that kind of invertible function H to convert all these points into the canonical space and union them together to get a canonical observation. And in the canonical space, you can use another like standard like point net or something to encode the geometry. And to generate the reconstruction, here is the occupancy field. You get some query position at the live frame. And you can also deform this query position to the canonical space and query a standard like occupancy network there. And the correspondence is much simpler. Given a source point of correspondence, you just convert to the UVW canonical space, and you do the inverse. And if you have correspondence, you can supervise it. If you ignore all this bottom thing and look into this green upwards block, you can realize the canonical shape, when trained on a lot of shapes, can have some interesting patterns that amplify the details of the geometry of this deformable object. And you can train this on many different like sequences. Here is the human body. And you can observe some interesting shared patterns between different individuals in the canonical space, which indicate maybe some kind of implicit cross-object correspondences. And this also works for animals. This is synthetic data deformation 4D, and the input is the depth point. Talking about the impact of this work, if you change the occupancy field into a nerve and supervise with rendering and optical flow, you will directly get, this is a very good paper, my friend made it, called Track Anything, Everything Anywhere All at Once, or OmniMotion, which it turns out to be 2023 SCCB best paper. So because this work is exactly the same deformation formulation, you can fuse all the small, noisy local optical flow into long-term trajectories that is consistent across long time and also through occlusions. But this OmniMotion has several issues, and we also have a follow-up to address it. So the main issue is like when a nerve first come out, it's very slow. Basically, for the OmniMotion, if you want to make it converge, it takes maybe 8 hours on several A100 for overfitting one scene. And also, this fitting is not always stable. That's to say, with different seed, random seed or initializations, sometimes the optimization may diverge. So this paper actually addressed these two issues by mainly improve the previous like invertible network with some more like design. Here is basically we are inspired by the all these kind of local features, hash tables, these local nerves, and there are two like improvements over the previous invertible network. First is we now don't do a standard MLP, but we can query some kind of hash table here, or you can think of it as a feature grid with this XY and get some like features independent to Z and plug into a small tiny MLP. And the second is previously we do a very simple affine function as Z plus T to transform the Z. And we can improve the expressivity by parameterizing this like function to a control point and a monotonic increasing function or decreasing function. So this small function is still invertible, but it increased the elementary expressivity of the whole deformation. The architecture briefly works like this. Well, first you have a video and you have a point. You also initialize this depth map per frame, and you can explore this prior from the depth images. So your unproject is through 3D, and you do the same thing. You deform to the canonical space, and you deform back to another type, and you can project, and you can supervise this with like any optical flow, or you can maybe do a much more long-term thing and supervise maybe with some kind of DIMO correspondences. And this is with this kind of first the better network, more expressive one, and using of the steps prior, which can be also optimized during the training, we can have a very high accuracy while use very limited time. Which this red line is this CaDeX plus plus the improved version, and this green line is the OmniMotion. And also because of this, this kind of depth prior, the optimization is much more stable. So by using different random seed, we can still get converged results, but for OmniMotion, you may get totally diverged results. For some challenging cases like this, this jumping motorcycle video. Okay, cool. So previously we discussed how we can use this invertible or build this invertible like nature into the deformation network. That is always very useful for implicit or volumetric rotation because you have query functions, densely deform things. Stepping into a more like recent literature where this Gaussian seems to like dominate everything, that nerve. Another thing that arises that is very important, that is the low rank nature of the deformation field. Especially when we are solving a highly dual-posed inverse problem. For example, fitting some Gaussians into one video or multi-view video. And this is DynMF, corresponds to dynamic motion factorization. So the idea or insight behind this work is, let's assume you have like a scene that there is a like outdoor scene, a car is driving, one car is moving. If you want to use dynamic Gaussian to represent this thing, there might be millions of Gaussians. because the background is super complicated. And to capture all that effect of the light, of the details, you need many, many Gaussians. If you make this like a dynamic Gaussian, which means you need to have different position orientation, at least for each Gaussian. There are many, many, many parameters. But remember, you are solving an inverse problem with only one video. They are very hard to constrain the solution space because there are so many parameters that is unconstrained. However, even this thing need to be composed by millions of Gaussians. The motion is very simple. Maybe approximately there's only one motion. That is the car motion, a rigid 6 number, 6 degree of freedom and change across time. So actually in real world, many motions, they are actually very compact and simple. Maybe they are just explained by several eigenmotion. Although the geometry can be complex, but the motion is simple. So this paper actually is driven by this insight that given, for example, this standard DIMO dynamic scene, you first represent as your a canonical reference with a standard 3D Gaussian. And then you only model very limited number of motion bases. Here in practice, there are 32 motion bases, which is parameterized by a small MLP. So basically, this motion basis is the MLP that inputs a query time. It outputs you 32 rigid transformations. And this will change by querying different time. This is a very compact motion basis that only contains 32 components. And we can easily compose a dynamic scene by a standard skinning, which means each Gaussian stores additional 32 real numbers and a linear blend this SC3 trajectory motions. So you can compose a dynamic scene by skinning these 32 eigenmotions. So interestingly, even with the 32 motion bases, this DynMF can reach state-of-the-art rendering performance, and you can get a very decent composition of the dynamic deformation field. And moreover, you can even activate a subgroup, a subset of the 32 motion bases, and form some meaningful decomposition, like moving one hand, moving one leg, or moving a specific ball. Which means this motion decomposition really makes some meaningful structure of this dynamic scene. And you can also move some undesired motion in the background at a more specific application. Cool. So basically, yes.
Yes, 132, because we also saw your result have some Zhejiang, maybe an arithmetical issue. Does that mean more basis means more smooth motion?
Yes, good question. So basically, that is just an example. Basically, we use 32, maybe 50 or something, that is hyperparameters. But with more motion basis, definitely you can get more detailed deformations. And we will see later in the later works, more advanced systems, you will use local motion basis, which may be 3,000 or maybe more, determined by the scale of the scene, that can approximate this kind of decompositions. Yeah.
Can I be like, if I increase the number of bases, will I start to lose the nice decomposition into parts?
Yeah, definitely. So basically, that is manually activated or grouped because this is unsupervised, unsupervised decomposition. You don't know which part
get correspondent to the.
Yeah. Actually, that part makes the student spend a lot of time to select which motion basis works on which part, but still. It at least shows some part of the motion basis are meaningful. And with more and more motion bases, you can think of this as if you have enough many, you assign each Gaussian a motion. Yeah. Okay, thanks. So this idea, we have discussed this idea for a standard nerve setting, where you have these permutations and you have multi-view videos, so you can fit the permutation into the video. This idea also can be used to do generation, and this is DIMO, correspond to diverse motion generation of arbitrary objects. So basically, the idea is very simple here. previously, when we talk about 4D generation, we generate one object plus one motion. If you want to generate another like motion, you run all these expensive diffusions, video models, all these things again. And by running this again, you have some risk to lose the identity of the object. Maybe the two generated one is not consistent to each other. So basically, this paper is studying whether we can generate one object plus a lot of motion, which spans a motion subspace. And the idea is first how we can construct like an object model with different motion. It's very simple. We just take the previous this idea of motion decomposition and condition this small motion basis network with some latent, like one latent vector for jumping, one latent vector for running, and maybe many other latent vectors for other motions, and share the same canonical Gaussian across different motion for the same instance. Second question comes, where does this motion pair comes from? Our hypothesis is the modern video models already contain a lot of like motion information for this specific or for many specific objects. So basically, you can like infer the video model with some specific design like prompt mechanism to generate many like candidate video for the same object that forms like a small data set of this object. And then you can distill everything end to end by like training this dynamic Gaussians, the motion networks, and this motion latent space. And finally, you can, once you generate, you can instantly sample many different motions, maybe in very fast way, and get different like motion of the same object. There are many other results like showing this motion can be interpolated in a meaningful way, or it can be also like joint embedded with language prompt. But this is something that's based on the idea of this kind of motion basis and forms motion latent space. Okay, so previously we have discussed how we use this global motion basis to either reconstruct dynamic scene from multiple video, or we generate some like object by still supervising from multiple video that's generated from video model. Note that when I mentioned the previous methods, they all depend on multi-view videos, because that initialization of the motion basis is not very easy. You need this multi-view stereo cues to like constrain this optimization. And this work is MoSca, which corresponds to motion scaffolds, is to attempt to solve a more like practical and challenging problem that how you can reconstruct the dynamic scene from real-world monocular videos. The different from multi-view video, monocular video is super challenging because the camera may only have a very small motion, while the scene have large motion, and you cannot depend on the classic like multi-view stereo cues to find the structure of the scene. And all this visualization are the results of this system. So specifically, the system deals with a problem that given an uncalibrated RGB video, which is actually a list of RGB images, the goal is to output everything. Basically, the camera poses, the dynamic foreground, the static background, and so you can render it from different viewpoints and at different time. Basically, you are solving, classically, this is called non-rigid SFF, before deep learning maybe. And this is extremely challenging, maybe one of the most challenging problems in previous computer vision. So the key to make this work stand on two sides. First is still we need to depend on some external knowledge. That is, with the recent progress of this vision foundation models, like the depth models, tracking models, flow models, to tackle this low-level vision task, we can reduce the solution space of this extremely challenging problem into a very handleable, like easy way. And the second is, given this kind of additional knowledge or information, we need a proper representation that can organize everything together and be optimized efficiently and regularized efficiently, because this is still a very high degree of freedom of the inverse problem, especially in the monocular case. And that representation is we call it motion scaffold, which is actually a graph of previously we defined motion, the motion basis. So it's actually a graph of motion basis that we can apply different regularizations onto it. And actually, classically, in graphics, this is called embedded graph or deformation graph, which is used in the classical dynamic fusion series of work that do the RGBD reconstruction of the dynamic scene. But here we are doing this with RGB videos and with Gaussians. So let's first see some results. Here is the result of reconstructing a Sora generated video. So on the left top, this is the input. And these are some closer view of this like frozen camera. And this visualization called MoSca is actually visualizing this kind of underlying graph that drive this dynamic scene. You can also visualize from farther view and see the RGBs, the solved cameras, the underlying graph, and the dense like trajectory of the Gaussians. And this is another example of the Sora generated video. It also works for some vertical videos. That this is some kind of like TikTok style short videos from the internet. And this is another example for this animal like video. Although I mean there are some artifacts because the problem is super like hard. You can see some artifact here, for example. And this also works for like a robot and some maybe movie clips. Also, this movie clip is a cherry pick result. It's not always that robust, I would say. I will skip this movie results. Okay, so we can do another like fancy application. You have a video that is like a ball game, and you can remove the hand and the cup and see where the ball goes because you can do the full 4D reconstruction. Although they have like artifact, this is super unconstrained. The ball is coming maybe a little bit with the mass. So how this thing should work? So basically, the main objective is to reconstruct this graph of motion basis that you can apply several regularizations onto it. I will briefly talk about the system because this is more like a system work and it contains maybe of 20,000 lines of code. But overall, in the first stage, you will infer 3 very important priors from 2D vision foundation models. The first is 2D pixel tracks. Now I can at the point we made the paper, we mainly use matrix depths because there's no conditional video depths. But now we can infer like video depths as well. And finally, you also infer the raft with some pairwise selections, and you can compute the epipolar error, which means you compute the fundamental matrix with a very robust RANSAC from OpenCV and measure how the flow agree with this fundamental matrix. And the more it does not agree, the more it's likely to be the foreground, which forms this epipolar error, which indicate the foreground. And after this stage, we can just forget about any models and we get this result of the tracks, the depths, and the epipolar errors. Then we can initialize the camera by solving a very simple triplet-based boundary adjustment. And you can also align a little bit the background. So after this stage, we can do the more interesting stage, which solves the dynamic problem. So basically, a motion graph is a graph of motion basis where the topology or the neighborhood is defined by finding the curved distances, which means if I clap my hand, the 2 points on my two hands should not be the neighborhood because sometimes they separate. So you can measure the distance across all the time on the curves to define which is the neighbor by a k-nearest neighbor. And you can later use this graph of motion basis, apply different like regularizations to skin the Gaussians. But at this stage, when you lift these 2D tracks with the depths into 3D to form 3D curves, there are 2 missing parts. First, if you want to animate the Gaussian with this motion basis, you must need some local frame. Actually, it's not just a point trajectory, but it's a trajectory with local frame. But point track does not give you this local frame. Secondly, the point track will also give you like occluded or invisible flags. Because in many cases, for example, in this like turning human, the leg turns to the back and it's not visible. You don't have any depth for it. So actually this part is marked as unknown. So what to do with these two parts? We need some kind of geometric optimization to initialize them with some physics-inspired laws. Basically, you initialize all the rotation. For simple for understanding, you just initialize them as identity, but actually there is a closed form solution to optimally initialize it. And you just connect the missing part as a line, as a straight line. By the
Can I just ask, are you doing like the minimal torsion frame across the curve or some other initialization? Like what is the initialization actually?
you mean the frame? You mean the rotation?
Yes.
You just find neighborhood and solve Procrustes.
Oh,
Weighted
okay.
Procrustes.
Okay, gotcha. Yeah.
And you just connect with a straight line as the initialization, and you can optimize the as rigid as possible, maybe the as rigid as possible, and also at the multi-level as rigid as possible on this graph of motion basis. And here's the visualization of this optimization. At the beginning, there are some straight lines because the point on the foot is turned to the back, or the track lost the track. And after the optimization, you can see this kind of straight lines gradually became a reasonable like rotating curve, and this is optimized graph of this like motion basis, like frame by frame.
Sure.
Yes.
So you decide like what are the lines within the CPU first, and then you do ARAP optimization. Is that the case?
You mean how to find topology?
Yes, I mean like how do you like you need to depend on other trajectories.
Yes.
optimize, right?
That is the topology of the neighbors of each trajectories. That is defined by finding k nearest neighbor in the curve distance space. The curve distance means the maximum distance across all the time of two trajectories.
Yeah.
And we mark something as neighbors only if it is close to each other all the time. That does not break. Otherwise, the hands will be connected.
Yes, so it depends on like some good visible points first.
Yes.
Okay.
Otherwise, if everything is invisible, you just have a degenerated solution that nothing is moving. Also, there are some like velocity or accelerations lost here, but the most important thing is this as rigid as possible. Because here we don't depend on any like external prior knowledge of the invisible parts. Because I can tell you maybe the most hard or the hardest, the difficulty in 4D mainly arises because of temporary occlusion. That is something previously seen by the camera just disappeared, maybe because of the motion of the camera, the motion of the object. Because for static, this is not a problem. You assume the thing is static. So when something disappeared, it's always stay there. And when you turn back, it should be stay there. But for dynamic thing, something disappeared. And when you look at it again, it may be a different place. So there is no prior of this invisible thing. And here, actually, we employ this physics as rigid as possible prior. But ideally, I think there should be some maybe video model or multi-view things to hallucinate it. And yeah, so finally, you can like grow the Gaussian. You can think of this scaffold as a tree, and you can grow many leaves on this scaffold. That is small Gaussians. You can back projecting all the frame steps into 3D, and all the points can be deformed to a target rendering time by a scaling, which means one Gaussian is ampered to 3D. It finds the nearest node at that time and associated with that node. By using the neighborhood of that node, you can do here is the dual quaternion blend scaling. You can think of as an advanced linear scaling. And by using the neighbor nodes trajectories, you can blend a smooth curve of that Gaussian. So basically, to give you a sense that the Gaussian maybe is 40 or 100 times more than the number of the trajectories. So the basis in this case is only maybe less than 1,000. Typically in the standard benchmark like the DieCheck, we have 3,000 motion bases, and the number of actual Gaussians is maybe 40 times to 100 times more than the motion bases, which means each motion basis carry 40 to 100 actually small Gaussians. And this is the full pipeline of the system. Yeah. Okay. I will jump this two parts and come to the final section of the talk. That's how we can exploit some kind of specific priors, because previously everything is general. We are talking about reconstructing general videos, and when we turn into more specific cases, because this might be maybe 80% of the real world videos. Why is it dynamic? Because there is a human, there is animal, there is maybe some movable object, and how we can exploit the category priors of this kind of objects. The first work is GART, Gaussian articulate template models. The idea is to exploit the very well-studied human model or animal models of category specific object. So the pipeline is very simple. So you have a simple model define a human skeleton, and you can initialize the Gaussians in the reference frame, which is defined by this template, and you can skin the Gaussians with a learnable skinning to different poses. But additionally, here is something novel, that is this template model usually works for tight clothes human. There's no significant problem when the clothes is very short and tight to the body. But in many cases, you have a long skirt, very loose clothes. This template model cannot handle that very well, and we just introduce some additional bases or these bones. Actually, the bones here is actually the motion basis we discussed before. And you can parameterize it with a small MLP and learn it. You can render it with standard Gaussian splitting and with some additional regularizations. Basically, these things work super fast. All the experiments are done on my laptop, not this laptop, but a gaming laptop. And it can converge when the poses are all aligned. You can optimize happens for at least 30 seconds, and it can converge to a reasonable result and can invert at more than real-time FPS on a laptop. This is the thing I mentioned, for the long skirts. At least you can reconstruct this additional, very challenging degree of freedom with our additional degree of freedom of that latent bones. But for the previous baseline, at that moment, a nerve-based one, you will create a lot of ghost artifact in the empty space, because these things cannot be explained by the standard template. And also, this work, I think, is one of the first one that demo this real-world dog example, saying this template model is not constrained to human, but also to animals. Also, this is some examples that we can plug the representations into a multi-video SDS framework, which means you just replace the real video, maybe a multi-video, here is MV Dream SDS framework, and do some text to avatar generation. Cool. So finally, here is I think the most strict prior, that is a multi-body system. So in real world, there is a very important problem to synthesize this articulated multi-body system, either for simulation, for robotics, for this interactive gaming. This is actually the first work in the modern deep network context to generate or consider the generation of this articulated multi-body object. Basically, the problem here is just opposite to the human one. Because for human animals, what you know is this is the human, and I know the skeleton, I know the structure of the object. What I need to do is to make that more expressive, to make it texture, to get details to it, but structure is fixed. Here for articulated object, the problem is the structure is not fixed. Actually, you can have 2-part objects, 3-part, 4-part, and different parts can be bound in a different way. They can be revolute joint, prismatic joint. So the key problem here is to study how we can capture this prior that has different structures. And the way we do that is we parameterize this into a graph. Actually, it's a tree because this is also the idea is used for like defining robots with the standard URDF format. Is a tree of link and joint. So importantly here, the node, one node in this graph is one rigid part. It has some attributes of the shape, the size, the position of the part, and the edge connecting two parts is a joint that defines the binding of the relationship between two rigid parts of where is this joint direction, what is the range of different components. And in this way, you can parameterize all the objects in the data set into a regular, that is a regular format or representation that is used for the network to learn or generate. So after you parameterize with a graph, you can easily do a graph diffusion. You can make it noisy and then learn the inverse of this noising process with a graph network. I will not go into the graph network detail here. But finally, after you train on data sets, you can generate like particular object unconditionally. Here, the graph shown here is a generated structure where the red edge is a revolute joint and the blue edge is a prismatic joint. This is an unconditional synthesis, but the useful thing is maybe you can do something more interesting like a condition on the same part and let it hallucinate different possible motion. For example, you have the same like parts. You can hallucinate different opening of the same dot. Here the condition is a very simple mask inverse diffusion, but there definitely have like more like classifier-free guidance you can make. Also, you can do something more crazy that you can dream about some static object's motion. For example, the motion of this mark might be turning the mark handle around the body. This is out of distribution cases because these things is never seen during training, and no one have annotated the articulation of a mark. For sure, you can do some other condition like the joint condition or hybrid condition and a joint. Okay, so I think we are time and thanks. This is the content of today's talk and this is the overview of any question I can take.
Also, it looks like everything is very consistent. So, you know, like line of work, very like solid and clean. So what do you think that like some extrapolation of your work, like next direction, like following
Yes.
this line?
Good question. So basically, I think there are several things that might be interesting, at least for me, in this 4D direction. First is you see this many different representations. Like you have general narrative, you have articulated, you have a lot of different works here. How to make this hybrid representations or unified representations for dynamic scenes? That is saying, for example, you allocate a proper level of degree of freedom to some subspace of the scene. Because we actually have a PhD student working on that now. You have a scene that have many human objects. Maybe there are some like very non-trivial like a soft object you need to use many motion basis to model. But when you identify the human, you should use a human template. Or if it's a multibody thing, you have to use maybe a per part rigid transformation to model it. So make this representation as compact as possible and hybrid. I think that's one like interesting part. How we can combine them together and get more like powerful and hybridized representations. The second is how to build a robust enough 4D co-map. That is to say, for now the results show, especially for the reconstruction of real-world videos, they are still not very stable. I haven't shown that we have at in a company level, we can run it on maybe several thousands of videos in a constrained setting, but still, this is not at a stage that the system can work on maybe any video on the internet. Because there are so many problems where the tracker fails, the depth failed, maybe the optimization have some corner cases. All these kind of things, they are not as something that we can deliver robustly to make it work at scale. So how we can make this robust 4D reconstruct system that can apply to general any video is still highly non-trivial. and it's relevant to many like fundamental problems in the in forward division, like how you can do better tracker, or efficient tracker especially, and how you can get maybe consistent depths at in a very efficient way, and it works in general different like scenario, not only maybe for indoor or outdoor, but in any kind of thing. All these things are highly non-trivial. And also, basically, we are working on something that's relevant to robotics as well. That how we can use this 4D perception of predictive model to help the robot to simulate the environment. Because maybe I can show you something. Yeah, basically, this is a project we are working on right now. First, there is something predictive model for the future. I was working in a company, but here is another project we call Robot Prompt, which says you can prompt the video models with some robot model and let the video model to hallucinate the change of the environment, which is very important for the task. I think most of these kind of 4D things very good for large space to show its ability is for robotics. Yeah, I think that is my current thought.
Yeah, no question. Yeah, as you mentioned, you want to do a general 4D co-map, something like that, right? How do you feel like MoSca 3R or Tutor or something like that? So it's kind of they are already general 4D co-map, right?
Yeah. So I'm you are asking some very accurate question. You want to ask me some like my review of the paper. But so first, this is the feed-forward model. Actually, I think this is the correct way. So feed-forward model is the correct way that can at least save you a lot of time during inference. For sure, you can do some post-processing after the initialization of this feed-forward model. Maybe a very lightweight optimization. Tutor, I think, is a good paper, but still, it's not working in general cases. At least for my experience, indoor thing is very good, but outdoor thing is a little bit suboptimal. Also, this area may need some significant effort to get data. We have data for 3D thing, but for 4D, annotated, even for camera pulses, we don't have too much of them. And if you have high quality annotated data for 4D, I think this feed-forward model can maybe must work. And also, you ignore the problem that, for example, for monster or all this kind of camera pose only matter. The fundamental question in 4D is not camera pose. There is only one fundamental question here. It's the track. This is the fundamental question in 4D. 3D track is composed of depth plus a very accurate tracker. Then there is no problem for camera. Camera is trivial, and for foreground segmentations, we don't need that. But the fundamental question is 3D track. If you can track accurately, you can get camera pose very easily. But still, we don't see very, very accurate 3D tracker at this moment. And they are very slow. But still, I believe the feed-forward is a correct, maybe, pipeline to this general 4D comment. Yes.
Thanks for the talk. Enjoyed it. A good question. I was thinking about MoSca, and it seems like what you're doing is you are basically structuring your motion space through these scaffolds, right? And that makes a lot of sense. The question is, this representation seems to be to some extent local.
You mean local?
Yes. Do you think there are any other directions, any other ways to structure the motion space that are maybe underexplored, such as hierarchical approaches?
Yeah, the hierarchical, hierarchical is something relevant to what I said, unified or hybrid, because you maybe have assign maybe a global rate motion for a car, and later you find there is a wheel on the car and need to turn. You will maybe assign some like maybe finer motion basis to some subparts. At this moment, we don't have, actually we have a PhD student working on like a rigid subclustering of the motion basis, but not for a hierarchical motion clustering. That is very useful for compress the representation, because now there are like thousands of motion bases, which is not always like necessary or like this totally more than the actual number of motion bases that required. But still, I think this is not a very significant problem at this moment, because the bottleneck is still like tracking at depth. But for sure, this makes sense, like hierarchical, because in the classical literature for deformation, there are like hierarchical deformation fields, like build coarse motion of the mesh and have finer motion on the local details. But I don't think we have too much paper even for reconstruction settings at this moment, because people are still considering how we can get even camera poses. Some people think this might be non-trivial. Yeah, so I think so for local, it has a reason, because you have to support locally. If you have a global motion basis, it's very hard to initialize. But I mean, regarding this representation question, I think there is definitely one thing that is not well investigated now. That is the light effect in the dynamic Gaussian. Because especially in many outdoor real videos, there is always shadows. And maybe there are light effects in the background. Now, you explain that like shadows, the background artifact with a deformation field, which means you have a shadow that's moving on the ground with you. How you can model this kind of time-dependent appearance change that is not caused by the motion? I don't think it's trivial now. And that may require also ultimately the representation of dynamic scene may not be a pure deformation based, because deformation cannot explain everything. There must be some hybrid of this time-dependent component plus deformation. And how to separate them is not trivial, because you cannot simply say maybe the motion, the color change on the ground is caused by a deformation or by a shadow. I may only see one or two papers in NERV study this, but still for dynamic Gaussian, this is ignored at this moment.
Okay, let's.
I'd like to have a follow-up question.
You may, excuse me, take that offline. Should be 2 minutes. Let's thank you.
That's
Thank you.